All right, welcome to lecture 6, I believe it is. I am recording this from my hotel room in Valencia, Spain. It's been a long 24 hours getting here, but it's a Sunday afternoon here, and I've got a little time to go ahead and put this lecture for you. So, again, I hope you'll be watching this with friends. You'll be pausing it to ask questions, to try things out in MATLAB, to try the equations yourself, and I'll be making suggestions as well where to do that. So let me start by addressing the question of, I'm going to start with the same thing we looked at last week, which was this particular this particular square wave that we tried to rebuild out of cosines. And last week I made a statement that I didn't really justify very well. I said we're going to only use integer multiples of certain frequencies, and I wanted to go back and talk about that a little bit. So let's start with this signal. This particular square wave has a period of 8 seconds. All right, and we just we can eyeball that we just eyeballed that. So that was fairly straightforward to work out. So when it came time to select whichever cosine I wanted to fit to this square wave, I said a reasonable guess would be to find some sort of cosine that has the same frequency as the square wave, because it certainly stands to reason that if this square wave has a period of 8 seconds, then there's probably a cosine in it that has a period of 8 seconds. So for that very first cosine, we said let's assume that that cosine also has a period of 8 seconds, and therefore it has a frequency of 1/8 of a hertz, and therefore it also has a frequency of 2 pi over 8, 2 pi f, which simplifies to pi over 4 rads per second. All right, so that's straightforward enough. But then, without a whole lot of justification, I said, for the next cosine that we want to test, we're going to do double that frequency. And I wanted to come back and kind of justify that to you a little bit. So the rationale goes like this. The square wave, the red signal that we're looking at, repeats every 8 seconds. And therefore, it stands to reason that whatever cosines we use to rebuild that square wave also have to repeat every 8 seconds. So for example, the blue signal repeats every 8 seconds. But let me show you another signal that repeats every 8 seconds. So what if I drew you this signal? Okay, so there's a cosine that it repeats every 8 seconds. It actually repeats every 4 seconds, but because it repeats every 4 seconds, it also repeats every 8 seconds. Okay, and so that's kind of a satisfying thing, because if you're trying to make a repeating signal, the red square wave that repeats every 8 seconds, the signals that you're going to use to build it had better also repeat every 8 seconds. Otherwise, it just doesn't work. So for this case, we're going to say this one had a period of half of that. All right, so this one has a period of 4 seconds, which means it has a frequency of 1/4 of a hertz, which means it has a frequency of 2 pi over 4, which actually I'm going to leave it at 2 pi over 4 right now, and you'll see why in a second. So let's say 2 pi over 4 rads per second. Okay, now let's go to the next cosine. Well, the next cosine that also repeats every 8 seconds looks something like this, and this one's a little trickier for me to draw. 2, 2, 1, 2. I think I did that right. 1, 2. It's a little ugly, but I think you get the idea. So that one has 3 times the frequency. It repeats 3 times in 8 seconds. So in this case, the period is going to be 8/3. Okay, so in this case, the period is going to be, instead of 8 divided into 2 sections, it's going to be 8 divided into every 8/3 of a second. It's going to repeat, which means its frequency is going to be 3/8 of a hertz, which means in radians per second it's going to be, let's see, it'll be 3 pi over 4 rads per second. And by now you can see a pattern. In general, we can argue that the nth cosine will have a frequency of 2 pi over t times n. Okay, so 2 pi over t gives us the cosine of the frequency of the first cosine, and then n means double the frequency, triple the frequency, and so on. And that's exactly what we have here. In fact, these cosines are so common that they have a special name. We call them harmonics. Harmonics. So we talk about the first harmonic, the second harmonic, and so on. So there you go. There's rationale for why we only have energy at integer multiples of that that base frequency. Now, there's a fancy mathematical thing that you can do to prove that all other frequencies, by definition, work out to zero. But that derivation is pretty boring and also beyond the scope of work for this class. So we'll say for all other omega, for all other omega than the ones above, A works out to zero. And that can be proven, but we're not going to prove it here. In fact, what's interesting is that even for this case, some of the harmonics can actually also have A equals zero. And we're actually going to see that in the example that, for the square wave that we're working. So our final and somewhat formal definition now of the Fourier series is, I'm just going to rewrite it a little bit differently than maybe what we've seen in class before. So how much cosine do we have at the frequency of the nth harmonic? Well, we have 1 over t times the integral over 1 period of x of t times, now before I told you it was e to the j omega t, but now we're seeing that omega is really restricted. Although in theory I could pick any omega I want, in reality I'm only going to be picking harmonics of the signal that I'm analyzing. And those frequencies are at 2 pi over t times n, and then t dt. Okay, so now if I substitute in the value of, I can leave n as a variable rather, and I can solve for a as a function of n. So let's go ahead and try that. Again, this is a bit of a rehash of what we did last Friday, but it's good to have a rehash. That's sort of how we learn things. So when we solved this integral last Friday, we found the following. We found that, we did the math. I'm not going to redo the math, but I will rewrite the answer. 1 over j, 2 pi n, times the quantity, 2e to the minus j, 3 pi n over 4 minus e to the minus j pi n over 4. I'm sorry, that's e to the plus j pi n over 4 minus e to the minus j pi n over 4 times 7. And I want to point out that there is an easier way. I mean, this can be simplified further. You can sort of attack this with a little bit more math and try to get it down into something that's a little bit more that looks prettier than what this expression is. But there's really no point. Like at this point, you can just put it into MATLAB, okay, or a calculator, and see what happens. And I'm actually going to take this moment to point out that you should get very good at working out how to do complex numbers either on your calculator or in MATLAB. But we're going to do this time and again this semester. We're going to be looking at complex numbers. We're going to need to know their amplitudes and phases, and you need to know how to do that. That can't be the hard part of this class. Okay, so with that formula in mind, let's look at the harmonics. So we know that the first harmonic means what we've learned is that corresponds to n equals 1. And the frequency of that first harmonic, in this particular case, is pi over 4 rads per second. Okay, and that's only because the period of our square wave is 8 seconds. If it had some other period, then this first harmonic would have some other frequency. And we've also solved, if you take n equals 1 and you plug it into that formula we have, and you do the math long enough, it should simplify to 0.64 angle 135 degrees, give or take. I'm sort of rounding, which it's a little inelegant, but it's nice to make the point here. Now, we learned earlier in the first week of class, we learned how to take a complex value of a and use that to express the cosine. So essentially what all of this is telling us is that the formula for the cosine of the first harmonic is 1.28 cosine pi over 4 t plus 135 degrees. Okay, so just to remind you, it's sorry, let me clean up that pi. It doesn't look very elegant. There we go. So we have the frequency. There's your pi over 4, and then remember this: the magnitude of A is going to be k over 2. So if k over 2 is 0.64, then k has to be double that, and then the phase angle we just read right off of the complex value. Okay, so that's what the first harmonic is. Now, let's go ahead and solve for a couple more. If we want to know what the second harmonic is, we do the following. We can say we let n equals 2, and we say that omega sub 2, the second harmonic frequency, will be 2 times pi over 4 rads per second. But then the really trippy thing is that if we take n equals 2 and we substitute it into our equation, we actually work out that a sub 2 equals 0. So in essence, this is not an error. What it's telling us is that this particular square wave doesn't have any energy at its second harmonic frequency. It's just a 0. Okay, now speaking of following along, you should be pausing this video and working out for each of these values of n. You should be figuring out some way of checking my math. Okay, you should be taking values of n and either plugging them into your calculator or plugging them into MATLAB to make sure you get the same answers as I do. All right, harmonic 3. So harmonic 3, by now, if this is all a pattern, omega 3 equals 3 pi over 4 rads per second, and A3 equals 0.21 angle negative 135 degrees, and therefore the third cosine will be 0.42 cosine, the frequency of the third harmonic, 3/4 pi t minus 135 degrees. Okay, and then finally I'm just going to do 4 and 5. We can show that for harmonic 4, we can show that A is 0. And for harmonic 5, we find that A sub 5 equals, let's see, 0.13 angle negative 45 degrees, and therefore x5 of t equals 0.26 cosine 5 pi over 4 times t minus 45 degrees. Phew! Okay, and then of course there's nothing to stop us from doing this, right? We can repeat this process for n equals 6, 7, 8, all the way out to infinity. Okay, so a couple observations. The first observation is that the amplitudes seem to be getting smaller. And this is, sorry, let me just write that. Amplitudes are decreasing. And this is something that we're going to find is true over and over again. In some cases, they'll be monotonically decreasing, which means that they get smaller and smaller with every single value of n. In other cases, we'll find that the values might get a little bit bigger, but then they'll get smaller, and then a little bit bigger, and then smaller yet. And in fact, as n approaches infinity, they almost always approach zero. So the amplitudes tend to decrease. And we're going to spend a little time thinking about what that means. The second thing I want you to notice is that we've discovered that in this specific case, our even harmonics, our even harmonics are zero. And that's interesting. Okay, there's a pattern there. And I'd like you to think a little bit about why that is. It turns out that if you go back to our original signal, the duty cycle is 50%. Okay, so duty cycle equals 50%. That means it spends 50% of its time high and 50% of its time low. And because it's 50% high, 50% low, we find that every other harmonic is zero. That's the pattern. So for example, if we looked at a signal which had a different duty cycle, so for example, if the duty cycle was 20%, so 1 part high, 4 parts low, 1 part high, 4 parts low, then we would find that every fifth harmonic is zero. Now that's not something that you really need to know, but it's kind of cool. Every fifth harmonic is zero. Okay, again, you don't really need to know that, but for those of you that are interested, that's kind of a neat thing to keep in the back of your head. That for square waves, there's that pattern with the harmonics correlating to the duty cycle. The next thing you should notice is that all the phase angles lined up perfectly. So what that means is that if you look at, we had 135, minus 135, minus 45 degrees, those are all going to contribute to make a bunch of cosines that are lined up exactly with the square wave. And we'll plot those in a minute so you can see it for yourself. But I always find that impressive. Like, we didn't really force that to be the case. That just fell out of the math. Okay, and then finally what I'd like you to remember is that ultimately you need all infinity harmonics. Oops, I don't know why it does that sometimes. Let's see. You need, it's even worse. Hold on. View 100%. You need all infinity harmonics. Okay, if you don't include all infinity harmonics, then the sum of cosines won't sum up perfectly to the square wave that we're trying to recreate. So here we are. We have just established that the square wave signal x of t equals, and I'm going to write this out. I'm only going to do this once because I'm trying to make a point, but it's sort of a point worth making. So essentially what we've just worked out is that x of t equals 1.28 cosine of pi over 4t plus 135 degrees plus 0.42 cosine, cosine of 3 pi over 4t minus 135 degrees plus 0.26 cosine of 5 pi over 4t minus 45 degrees plus dot, dot, dot. Okay, that's essentially, I'm just re-saying what we've already worked out, that x of t can be expressed as the sum of cosines. And the reason I'm saying this is because now, if I ask you to give me the frequency plot of x of t, you know how to do it. You would draw me one set of j omega axes that correspond to the magnitude, and you draw me one set of axes that would correspond to the phase. And now look what's going to happen. Look how cleanly this is gonna fall out. Okay, the first cosine has energy at pi over 4 rads per second, and the magnitude of that energy is 0.64. Remember, if this is k, then we know that A equals k over 2 e to the j phi, and we know A conjugate equals k over 2 e to the negative j phi, and we know that A tells us how much energy we have at frequency omega, at frequency j omega, and A conjugate tells us how much energy we have at frequency negative j omega. So, according to this, at frequency pi over 4, I have an amplitude of 0.64. So let me pull up my notes here. 0.64. And at frequency minus j omega, I also have the same amplitude, okay, because it's k over 2 for the positive frequency and k over 2 for the negative frequency. Okay, and that all corresponds to the first harmonic. Now we can look at the third harmonic. The third harmonic has energy at 3 pi over 4. How much energy does it have? It has half of 0.42, so that's 0.21. And that's at frequency 3 pi over 4 radians per second. And then I'll do the same thing over here at negative 3 pi over 4. And then, so that'll be, the blue will be that one. And then finally in gray, we'll do the 5 pi over 4. And that will have an amplitude of 0.13. 0.13, and that's at 5 pi over 4. And then we'll have the same thing over here, minus 5 pi over 4. And you get the idea. And of course, there's going to be more and more. It's not just these ones. They're going to go in perpetuity on either side, but since I'm doing this by hand, I'm only going to do those harmonics. Okay, now let's look at the phase angle. For pi over 4, we have a phase angle of 135 degrees. At negative pi over 4, we should have a phase angle that is negative of that. So it should be negative 135 degrees. Okay, at 3 pi over 4, we have a phase angle of negative 135 degrees, which means at negative 3 pi over 4, we should have positive 135 degrees. And then finally, at 5 pi over 4, I should have a phase angle of minus 45 degrees, which means over here I should have positive 45 degrees. So this will be minus 45 degrees and minus 135 degrees. And again, those are also going to continue in perpetuity. And that is the frequency plot. So in essence, what we've done now is we've gone all the way from starting with a plot that's a function of time, and we've converted it into its equivalent representation that's a function of frequency. And in fact, what's really cool about this is that if I were to just show you the frequency plot, you could actually work all the way backwards and get the time plot, because now you know how to interpret these sticks, how to look at these plots. You know, each one of these points represents a cosine. You can work out the frequency, the amplitude, and the phase of each of those cosines. You do that, you repeat that process for each of the sticks, and then you go and you add them together, and you've got your time signal. Okay? So, so we're in good shape. So, okay, so let me do a couple quick things for you. So the first thing I want to do is some MATLAB plots. I actually want to plot the magnitude and the phase. I actually want to do these same plots that you're looking at. I want to look at them in MATLAB, just so we can go through the process of how to create a bit more of a professional looking plot. Before I do that, I just want you to notice one final thing. which is that for both of these plots, there's a bit of redundancy. So if you look at the magnitude plot, you'll notice that it's even. So in other words, if I showed you the right-hand side of the plot only, if I only showed you the positive frequencies, you would know what the negative frequencies look like. It's always going to be the mirror image. And then likewise with the phase plot, if I showed you the right-hand side of the plot, you could work out what the left-hand side of the plot would be. It's not quite the mirror image, it's the negative mirror image. Okay, but in other words, if I showed you just the 135-degree stick, you could figure out, well, you could infer that there would have to be the equal and opposite stick at negative frequencies. So sometimes for expediency, we don't even bother plotting the negative frequencies, okay? And it's not because they're not there. They're absolutely are there, okay? You must have negative complex frequencies to cancel out your positive complex frequencies. But just for the sake of clarity a little bit, sometimes we will not show the negative frequencies because they really don't add anything to the plot, right? They just take up space without showing us anything that we didn't already know. Okay, so let's go ahead and grab that formula, and I'm just going to type it in again. So, oops, let's go to MATLAB. So clear, and A equals J times pi over 4. Okay, so I'm going to make an n vector. I'm going to say I want the first 100 harmonics. So right now n is, when you write n this way, you get n equals 1, 2, 3, all the way up to 100. Actually, let me go ahead and let me increase the font on that real quick, because I'm sure someone's going to complain that they can't read that. Where is it? Fonts, and let's up that to like 14 or something. Okay, all right, hopefully everyone should be able to read that. Okay, and then A equals 2 times, let's make sure I get this right. Okay, e to the minus 3a, is it e to the minus, 3 times a times n, minus e to the a times n minus e to the minus 7 times a times n, divided by 2 times j times pi times n. Okay, and let's actually before we plot A, let's plot the cosine itself and let's make sure we type this equation in right, because if we didn't type it in right, it's not even worth doing the plot. So let's do a loop. Let's see. So let's start by initializing my square wave to 0. And I'm also going to need a time vector, and I think I'm going to go from, let's have it span, I don't know, minus 20 to 20 seconds. That should give us a nice big range of numbers to see our signal that has a period of 8 seconds. And let's just cram a bunch of points in my plot so it's pretty. Let's put 10,000 points in the plot. Okay, and now we can iterate through the loop. So for I equals 1 to 100. So we know that the frequency is going to equal 2 times pi times the ith value of n over t. Okay, and let's tell it that t is 8 seconds. And then we know that k is going to equal 2 times the absolute value of a of I, and the phase angle is going to be the angle of A of I. So when I say A of I mean the ith value of A. So if I'm going in a loop, first I'll hit the first value of A, and then the second value of A, and then so on. And now I can make my cosine. So x equals, so I want to make a running sum. Take whatever my existing value of x is, and add into that k times cosine of omega t plus phase, and plot the result, t comma x. Bang! Look at that. Okay, right on the money. All right, and once again we can see that it's not exactly a perfect square wave, and the reason it's not a perfect square wave is that I didn't go all the way to infinity with my harmonics. I only went up to 100, but that's still pretty good. If I want to label my plots, I can do x label, time, and maybe I can add a title. So title, reconstructed square wave. I don't know, whatever you want. Okay, make it look professional. Good. So now that I know for sure that I have the correct value of A, that I typed it in properly. And again, I know I typed it in properly because I used it to reconstruct my square wave, and I in fact got the correct square wave. I'm going to take that and I want to plot the magnitude and the phase. So let's do this. Before I do that, let's make sure that this square wave always goes in figure 1. So in MATLAB, if you say figure 1, essentially what you're doing is you're saying create a figure, create the first figure, and this is where the plots are going to go. And it's always a good practice before you plot in your figure to execute the CLF command, which means maybe there was something in figure 1 before from something you were working on yesterday and you forgot about it. Clear figure guarantees that you're going to delete whatever was in figure 1 and you're going to start on a clean plot. For the amplitude and phase plots I want to do, I'm going to put those in figure 2. Okay, so here's figure 2. And let's get started. So, what I'd really like to do is make a lollipop plot, and I'm going to sort of do it wrong 2 or 3 times and sort of work up to the correct representation. So one thing I could do is I could say, give me a stem plot of the absolute value of A. So remember, A is these 100 values. Because I have 100 values of n, then I have 100 values of A that correspond to those values of n. And if I want to look at just their magnitudes, I can say, give me the absolute value of A. And if I do that, here you go. And in fact, you can tell right away this is correct, because if you look here, this is our value of 0.64 that we were predicting in our plot. Let's see where our plot is. Can I move this? Is this thing still alive? Right, so I'm expecting the first lollipop to have an amplitude of 0.64, and then 0, and then 0.21, and then 0, and then 0.13. And there you go. So there's a 64, 0, 0.21, 0, 0.13, 0, and so on. So these are the correct values. So I'm happy with the amplitudes. What I'm not happy about is the phases, is the x-axis. So right now, if I just say, give me the stem of A, it's just going to plot it versus index number. So this first stick will be, the x value is 1, because it's the first element in the array. And this stick will be at 3, because it's in the third element of the array. Which is okay, but what I really want is frequency on the x-axis. So the solution to that is I'm going to create a frequency vector called omega, and that frequency vector will be 2 times pi times n over t. Now remember, n is an array of from 1 to 100. It has 100 elements in it. And so if I define omega like this, it will give me a corresponding array of 100 values of omega. And now I can stem omega against A. And now my x-axis is done appropriately. So for example, if I zoom in a little bit, you should see that my first stick it should be at a frequency of, what do we say the frequency should have been? Pi over 4 rads per second. And pi over 4 rads per second is about, that as a decimal, it's 0.78. And so there you see, there's the 0.78. Okay, so now the frequencies are appropriate. So in order to make sure that everybody knows that, we're going to label the x-axis as frequency in rads per second. And we'll do a y label of amplitude. Okay, so now everybody knows what this plot is. Okay, now the final thing we need to do is the phase angle plot. So I'm actually going to, let's see, we could probably cut and paste a lot of this. So let's make a figure 3. I don't need to redefine omega. It's already defined. It's going to be the same thing. And let's call this angle. And label it phase angle. Okay, and there we go. Now that's not wrong, but there's a couple things I don't like about it. The first thing is that I want it in degrees. Sometimes I want it in degrees, sometimes I want it in radians, but whatever. The diagram I did back on my notes was in degrees, so I'd like this one to be in degrees as well. So I'm going to go ahead and multiply by 180 and divide by pi. Alright, and so now at least it matches. The first stick is at 135, and then negative 135, and then negative 45, so those are all where they should be.
But the real thing I'm unhappy about is that it's often very helpful to see the two plots side by side. So you can see here where I drew them, I had the magnitude plot on the left and the phase plot on the right, and so on. So I want that here. So really what I want to do is I don't want to create a figure 3. What I really want is to do the magnitude and the phase plot both in figure 2. So what I'm going to do is I'm going to take advantage of the subplot feature in MATLAB. And here's how that works. Before I do the plot, I'm going to say subplot. And then what I want you to imagine is that I'm going to take this figure window and I'm going to break it up into a grid. I can have as many rows and as many columns as I want. So for now, let's say I want 1 row, 2 columns, and I want to have my next plot go in the first box. Let me just comment this out. So if I plot that, you can see that my amplitude plot has now been squished all the way to the left. So you can imagine that what I've done is I've created a grid where there's 1 row and 2 columns, and then I said give me the first plot in the first position. So then, when I go to do the phase plot, I'm also going to use the subplot command, but instead of putting it in the first spot where the amplitude is, I'm going to put it in the second spot, and now they're side by side with each other. And I know it looks a little bit cramped, but if you were to undock that figure and sort of blow it up to screen size, it's actually quite nice. Okay, and this is how you can make a nice side-by-side plot. Now in reality, you can make any dimensions you want, right? You can do, 3 rows by 4 columns, and I mean at some point it'll get a little ridiculous, but it'll give you whatever you want. All right, but I'm going to stick with 1 and 2 for now because that's what makes sense in this particular situation. Good. All right, so we're almost done. So so make sure you can do all that. The last thing I would like you to do is I'm going to give you another signal, and I want you to kind of go through all the same steps. So let me draw that signal for you, and you see if you can work it out. So the final signal, the final thing we're going to work on today. So here's a signal with respect to time, and let's do this. So let's have a little pulse here with width. It'll go from 1 to 2, and we'll give it a height of 1. And then it will repeat from t equals 8 to 9, and so on. And I guess on the other end, it'll repeat from -6 to -5. So let me see if I can draw that properly. -6 to -5. Let's double check the math. That looks good. Okay, so this is x of t. So here's what you should try to figure out in this order. Okay, first, what's the period? Secondly, what is the frequency of the nth harmonic? Thirdly, what is a sub n? And remember, you don't ever have to ask me if your value of a sub n is correct. Okay, you can always go back to MATLAB and do something like what you see here on line 5, lines like 5 through 15, and just make sure, just try it yourself. Okay, if it works out, if you get the same thing back, then you did it right. If not, then you didn't. Okay, give me the magnitude and the phase for the third harmonic. Okay, so make sure you can get the numerical values for that. And then finally, can you create a plot of the magnitude of A versus frequency and the angle of A versus frequency? If you can do all those things, recitation should be a breeze for you, and you'll have a really good understanding of all these things. I'll have a follow-up lecture for you on Wednesday, and I'll actually, before Wednesday even, I'll post the solutions to all of these questions. I prefer that you not look at the solutions before you work them, so maybe I won't post the solutions till something like Monday evening or something, so you have a chance to wrestle with these during lecture. But again, you don't need me to prove that they're right. You can check your own work essentially using the techniques that I've showed you. So I'll post solutions for that, and then on Wednesday we'll kind of take it to the next level. In the meantime, if you have questions, just keep emailing me. I know a bunch of you have been doing that, and it's been a fun process. And we'll take it from there. Thanks very much for indulging me for trying to watch the lecture in this fashion. I know it's not perfect, but I'll see you on Friday. Thanks.